Our next speaker is Professor Sunita Sarawagi from IIT Bombay. She's Institute Chair Professor at IIT, and her work has expanded a whole host of fields in computer science, starting from query processing in very large databases to information extraction, and more recently Markov random fields. And today she's going to be talking about something different yet, which is deep neural networks.
Hello. So I'm going to talk about two things which will make the deployment of neural networks more broader. You know, it will sort of apply to more general scenario after all the efforts that are spent in training neural networks. So in fact, my talk is actually a concatenation of two distinct talks. So first, I'm going to talk about how you can train neural networks to generalize better to new domains. So there have been, of course, many of you might have seen, there are a lot of recent press articles about how neural networks are easily fooled by adversarial examples. So this is some work which is sort of addressing one part of the problem, which we call domain generalization. And then in the second part, I'm going to talk about calibration. So the problem that we are interested in here is a new kind of generalization. You know, generalization is the bread and butter of learning, machine learning. But here we are talking about a notion of domain generalization. So the problem setup is as follows, that during training, you are given data where in addition to the input X and the correct label Y, so we are considering standard classification problems. So with every input X, you have a label Y. And in addition to these two information, you are also given a domain label. So, so examples of such data would be, say, suppose if you're trying to train an OCR model, then you would have data corresponding to images and the corresponding character label attached with each image. That is the standard XY pair that is given to you. But in addition now, we have a font label, which will tell us in which font this particular character is written. So you can think of font as a domain. Okay? A second example, say consider the training of a speech recognition model, where you have the input, which is the speech, the audio spectrogram, and the label Y, which is the spoken word. And in addition, you have a domain label, which says the speaker who is speaking that voice. So here, speaker is the domain. Now, this problem is particularly relevant in the case of training modern deep networks, because these necessarily require such a large amount of data that your data often ends up being a union of data from multiple domains. So you generally, your data essentially is a mixture of data from multiple domains. So in such scenario, we want to train a model to generalize to new domains without requiring a distinct adaptation phase. So domain adaptation is a well-known substream of machine learning. I'm not talking today about domain adaptation. So our deployment scenario is as follows. So during training, we are given what we call this now multi-domain data. But at the time of deployment, we are given an input X and we are seeking its label Y for an isolated instance X without giving any information about the domain. And in fact, X can come from a domain which is outside the training domain. So that is the problem. So we want to train a model which can exploit the variations that come out of changing domain IDs in the training data to plan to handle new domains at the time of testing without having an offline domain adaptation phase using either labeled or unlabeled data in the new domain. Yes. 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 That's right. Yes. Which domain? Yeah. So, but a better motivation. So, Devrat, I don't know if you heard his question. Thanks for, I just want to make sure everybody understands my problem better. So, he asked for this setup where you have two domains. But the problem scenario we are targeting is where during training you have multiple domains, like say 50 to 100 domains. And you want to sort of capture some, you want to study how the data changes when you go from one domain to the next and train models which can therefore handle new domains at the time of evaluation. Is that clear? So this is the problem data. So now the question is, how is this requirement of generalization any different from standard notions of generalizability which characterizes the whole of machine learning, right? That's what all the pack bounds and other bounds are for generalization. Now, when we talk about domain generalization, the problem is actually quite different. And the closest analog I can give to classical supervised learning is, say, if you have in your data one categorical attribute where the domain of values in that categorical attribute is open-ended. So like you are creating, say, a standard classification model for risk estimation, and you have one attribute which is the highest degree of a person or the employment of a person, and then the set of employments, all of it are not seen at the time of training, and a typical supervised model just treat such new domain members as unknowns, right? So you have an UNC value. Like in text data, you always face unknowns at the time of deployment, and you just leave it at that. Okay, we want to do better than that. We want to come up with a way to generalize for unseen categorical ID, not continuous IDs. Domains are to us, up to what I have described so far, categorical values. There is no other information attached with the domain, and we still want to generalize to new domains. And we want to do better than just treating the new domains as unknown values. Okay? So that is categorical, means these are incomparable discrete values, like say color or profession, education, yeah, such kinds of values. So is it even possible to come up with a notion of domain generalization? So we were struggling with this problem for a long time until we looked at this from a Bayesian perspective, and then we started getting some handle on what does it even mean to generalize to new domains. So this is our Bayesian characterization of domain generalization. So first, let's consider the Bayesian network corresponding to standard classification tasks, where you have X, which is your input variable, and Y, which is the class label. And you believe that the X that you observe is a function of a hidden label Y. And during training, depending on what method you use, whether a discriminative method or a generative method, let's say we are using a discriminative method, you try to model probability of Y given X. And for this training to be even well defined and to be estimated well, you require that at the time of training, you see labeled examples for each discrete Y. Right? If you do not observe examples from a particular class label, you will not be able to predict that class label, as simple as that. Okay. Now, when we are talking about domain, in the presence of domain, we believe that X is an intricate, inseparable function of Y and D. Okay. So going back to the font example, the image that you see of a character is a kind of a difficult to separate out function of the character itself and the font. Like a cursive A will look very different from a Times Roman A, and in spite of all the recent work on style extraction in neural networks, it's really difficult to take out the cursiveness from a cursive A and transform it into a Times Roman A. So that was our starting premise. We initially thought that somehow you can take the style out of a character, But as you must have discovered from Calvin and Hobbes, you can take the jungle out of the tiger out of the jungle, but you cannot take the jungle out of the tiger. Similarly, so we could not extract the size. So basically, x is an it's a complicated function of y and d. And now, for estimating the probability y given x distribution, for standard Bayesian network, we know this is a V node. If I have to estimate probability of y given x, and if x is a function of both y and d, then you have to have in your samples all distinct values of d, right? Otherwise, you cannot estimate the distribution. So essentially, I am interested in estimating probability of y given x, and because d is discrete, I would have to sum over each distinct value of d and do this summation, right? This is a discrete summation problem. And if I do not observe all members of this domain of my domains, then I cannot do this aggregation. So how can I even generalize? Because in order to define a well-formed learning problem, probability y given x has to be estimated well. And so that is not possible. So how can we even generalize? So this is our first insight. What we claim is that if you could somehow, we don't know how, but if you could somehow insert an intermediate latent continuous variable, okay, so G is some multidimensional continuous variable which captures the properties of domain. And let's assume that you have enough distinct Ds, and by some way you are able to estimate PG, the probability distribution over these continuous latent attributes of domain. Then there is some hope of estimating probability y given x, because now probability y given x, instead of being a summation over distinct domain, is an integration over the space of G's. So here what our premise is that every domain is actually a point in this multidimensional continuous space of G attributes. So although we will never explicitly name the attributes, just to give an example, like say when we are talking about speech recognition, we can think of G's as representing properties like the accent and the tone and the frequency of the voice, okay? And we accept that these are unobserved variables and we would like to estimate them along with estimating probability y given x. So how can we do it? Yes. There is that's right. Few samples of the domain. That's right. So any new domain is a point in this G space. Yeah, they are finite. They are finitely enumerable. Yeah. But how do we, I mean, we don't want any supervision on the G space. Okay? We just, so it's like we are given naturally domain separated data. That's it. So this is the Bayesian part. So once we were able to draw this Bayesian network, we thought, okay, now let's go into neural networks. So now we'll talk about pragmatic. How do you actually train a real neural network? Say like suppose if you have a CNN-based image classifier, how can you apply this Bayesian network concept to train it for better domain generalization? So there, now how do you capture G? Okay. So how do you find out what G is? How do you, sort of supervise the extraction of G? So here what we did is, we have this method which we call the CrossGrad method, and here is the architecture that we follow. So you have an X, and from the X, so you hear this part of the network, which is this left part. This is your standard classifier, which we are denoting as C theta1. So this is the classifier, and this is the label classifier's loss JL, and it's supervised on the correct label Y. And now in addition, what we do is from X, we use another neural network, and that neural network's last layer gives us G. And in order to make sure that it is G and not something else, we have a domain classifier which sort of tries to predict the domain label from this G. Okay. And so this is, we just use another neural network to extract G from X. And now, so that is just the simple initial architecture design. But the important thing is, how do you train it so that it will actually keep G and not label another thing else? Yeah. Yes. Gee, that's a very good point. I was hoping no one would notice it. Yeah. Yeah, the fact that Times Roman and Helvetica might be almost the same, and you don't, so for the moment assume that they are distinct, that they are different. Otherwise, it would not make sense to have a classifier loss on. Capital J, it's just the loss, the log likelihood, the loss during training. Okay, so that is, it's the SVM legacy. Yeah. So the D is known at the time of training. Yes. Yeah, and that's what G is. So therefore, G will capture the domain, because you will, on top of G, you will just have a standard, just a softmax loss to predict D, the domain loss. So that's how you are getting G. But what is preventing the label information from leaking into G? So for that, we do some adverse. That is the main thing. So so those things I'll clarify. So the main thing. So now, okay. So first I will tell you how do we generalize to new domains. See, even if you just have the G there, it still does not ensure that you can generalize to new domains. In fact, when we first trained this network with just this part, it was overfitting very happily on the training domain. So this is in fact the second place where we felt that a light lit in our head, which is that in order to generalize to new domains, you have to hallucinate new domains. So we sample new Gs. So we hallucinate new domains, and so you give a training example. From there, we will extract its G, and then very conservatively we'll move around near that G, and we hope to hallucinate new domains in the process. And then the new hallucinated domain will be, through some inverse Jacobian method, transferred back to X. So we require some kind of inversion here. So we'll transform back to X, and that new X will be used to train the label classifier. So that is the key to generalization. That we think of, because we have come up with a continuous representation of the domain, we can jump to new domains and train X's with those domains. Now, of course, this is better said than done, because how do you know that the X that you are hallucinating are not all garbage? So therefore, we take very tiny steps. X. Yeah. Yes. G, actually, it's problem dependent. So again, we had all fun with tuning various, and that now we are getting into neural network land and all these joys of hypertuning and all. Yeah. No, it's not 1 or 2. It's more like 16 to 32. Yes. Huh. See, actually, we did not want to use GAN. Somehow, in my experience, GANs works for people who are very GANny. But somehow for me, it never works. Okay, I don't know. It's just we have tried in so many different ways. I just feel that I'm just not good enough for GAN. It never works for me. We tried, many different versions of adversary. It works for people. I'm not doubting that, but it's just very difficult to get it to work. Yeah, to adversary. Yeah. Okay. So it did not. We tried such versions, and it didn't work. So basically, so this is the main thing. So we sample new Gs. So how do we sample new Gs? Here again, so here we use adversarial training. So this is different from GAN, which is that Goodfellow has this 2014 paper where they perturb X based on, the gradient along the label. And so that way they claim that you have more robust classifiers. So we do the same thing, except that our adversarial perturbation is along the domain loss. Okay. So we sample new G by adversarially. I'm so sorry that this is coming in here. Oh no. So yeah, I should perhaps try to. No, but I think this one will come up. I should. Yeah. So now, so this is the whole our training methodology. So we take X, and then from X we will get the G, and now we will calculate the loss, compute the gradient, and get a new G, and that will be transformed to the X to get a new X. So that will give us an X perturbed along the domain loss. But in order to make sure that this branch does not have label information, when we train this branch, we also feed to it X's which are perturbed along the label loss. So this way it's a symmetric network. So we perturb X both along the domain loss and the label loss, and we feed it in the cross way. And that's how we get 4 types of losses at the time of training: the standard label loss, the newly added domain loss, plus the label loss on X perturbed by domain loss gradient, and the domain loss on X perturbed by label loss gradient. Okay, so this third term makes sure that this label classifier does not overfit on the domain. It can handle new domains. And the second term, that last term here, makes sure that this domain classifier does not encode label information. So this is what, and this actually worked. I mean, we did not get mind-blowing improvements. So, but yes. Yes. No, we do not want to change its label. See, that's why we do very cautious perturbations. When we perturb along the, so here, when we perturb along the label loss, that time, we take small steps. And here also, this network we train so that it will not change the label when you change the domain. Well, actually, say if the Goodfellow, the standard adversarial training also, they do a small perturbation along the label loss. So the epsilon is controlled so that you do not change the label. Right? Okay. So, the GAN equivalent for domain, this is called the domain adversarial network. This is what everybody uses. Anytime people talk about domain adaptation, everybody just thinks about wiping away domain, whereas we talk about keeping domain because we want to provide high accuracy even for the training domain. And sometimes, very often in fact, your input examples are very intricately mixed with the domains, and if you try to separate them, your label accuracy might drop. So in fact, after this work, I am totally against any attempt to trying to wipe out domain labels. Keep your domain labels, make sure you generalize to new domain. Yes, that's it. Yeah. Yeah. That is absolutely the assumption. If that assumption does not hold, then this method would not work. That's it. Yes, just it. It's embedded in X. Yes. Yeah. And so the interesting thing is, so many people talk about wiping away the domain. We found that by feeding the G into the label classifier, we got a small but consistent improvement across all 4 tasks that we tried. It just shows that the domain label is very important. In fact, and if you give it separately, it helps it even more. Right? Yes. So actually, we thought it's one-off because very often when so these large-scale examples of say OCR or speech recognition, we all just believe so much the FAN companies to provide us trained models, right? And now, you would not bother to customize a speech recognition system or an OCR system to your domain, right? You would expect it to work out of the box. So there are enough motivating applications. Right? Yes, yes. That's right. Yes, you could do better. Yeah, yeah. But, I think even this is a very common situation where you face examples one-off. Right? Principles. So one thing I'll tell you, see, I am actually not a theoretician. But when these guys invited me, I said, look, are you sure you want me? So I don't know what you mean by principles. For me, what I presented was principles enough. Sorry. I mean, really, I am not in this crowd. I mean, I am not a theoretician like the way you people are theoreticians. Right? I understand a bit of graphical models. And, I'm a computer scientist. I told them, like, are you sure you want me? Okay. So, so we